So during a recent trip to the local university, in which walking about the campus was the order of the day, my walking companion, a fine young lady, was struck with a bit of nostalgia, reflecting back on her student days. And such has thus inspired me to reflect upon my own. And considering this channel is fairly well steeped in science history, I thought I'd share a clever little mathematical trick that I discovered when I was a freshman in college that was authored, I believe, about a little over 100 years ago. So without further ado, let's take a look at time dilation in special relativity. The tools we're going to be using to recreate the construction of Einstein or Lorentz's equation that governs such will just be basic algebra and basic trigonometry. There will be no need for tensor algebra or tensor calculus, which is more concerned with general relativity. The focus of time dilation is just comparing and contrasting the time it takes for a particular single event to occur in two Cartesian coordinate systems when one system is in motion relative to the other one. So basically, the time it takes for this single event to occur is a function of where the observer is regarding the coordinate systems. Is the observer in coordinate system 1, or is the observer in coordinate system 2, which is in motion relative to system 1? And we'll be defining a function that specifically does this, where we can plug in the time it takes in one system and the velocity of the system relative to the other system, and then we'll be able to figure out the time it takes in the latter. Imagine you are an observer in a moving train car. You are on the inside, and you place on the floor of this train a flashlight which is pointing upwards, and directly above the flashlight you place a mirror on the ceiling of the inside of the car. Then for one brief moment you turn on the flashlight such that one photon is released from it. The photon travels to the mirror, bounces off the mirror, and returns back to the flashlight. That is the particular single event that we're going to be focusing on in this thought experiment. And in order to construct our equation, the first question we must ask is, how much time did it take for the photon to travel from and back to the flashlight? And for that we need to know two things. Firstly, the distance involved in the travel of the photon, and we also need to know its velocity. I've already notated that the distance between the flashlight and the mirror is a component we will call d. So we know that the photon traveled up d and back down d, so therefore we know that the distance traveled is 2 times d, or 2d. And we also know that the velocity that the photon traveled is c, the speed of light. And with a tad bit of dimensional analysis, we can multiply 2d by 1 divided by c, and that will give us the time it took for the photon to travel its path. Or in other words, because c is defined as a particular distance over a particular time, then what we can do is flip that d and that t to where the t would be the numerator and d would be the denominator. And we do that specifically so when we multiply by 2d, the d's cancel themselves out and we're just left with a time component. That way we can examine the time it took for the event to occur. And for the purpose of our thought experiment, we're going to rename delta t prime. And we're going to clean up the notation on our first equation just to make it a little bit neater. So this is all that needs to be said regarding observing our particular single event in this Cartesian coordinate system. So let's take a look at what this selfsame event looks like when observed from a different vantage or from a different Cartesian coordinate system. This time we're going to be outside the train. Maybe the train has a big window and we can see what's happening from the side. And we're going to be watching the train move by from left to right. And as it's moved by, we've observed 3 snapshots in time, like to taking 3 separate pictures of the train as it moved by. The 3 frames are significant in that they help us watch the path of the photon as it leaves the flashlight, hits the mirror, and comes back down. In this vantage point, we see that the photon does not travel straight up and down, but travels in a diagonal fashion secondary to the motion of the train. And just like we did before, we're going to ask a time-related question and ask, so how much time did it take for the photon to travel the path defined by the motion of the train? But before we tackle the mathematics of this part of the thought experiment, we should note that there is a curious discrepancy happening with regard to distance concerning the 2 vantage points we are examining. Observe that the distance between the flashlight and the mirror has been preserved in this present vantage, but the distance of the path of the photon defined by the motion of the train has been elongated relative to this simple distance. And we know from trigonometry that the d prime in our example will always be greater than the vertical d, or d between the flashlight and the mirror. And we should further note that even if the train's velocity started to approach the speed of light such that the train became compressed in length along its direction of travel, that this trigonomic principle is preserved because the d prime has a vertical component in its vector. One of Einstein's greatest insights is that he assumed when authoring his equations that nothing can move faster than the speed of light, and thus far nothing in our physical world has challenged that assumption, therefore leaving us to question, how does a single particular event, the photon leaving the flashlight, hitting the mirror, and coming back, occur seemingly simultaneously from our 2 vantage points, yet from one it has to travel a greater distance than from the other. The only component left in the system that can be modulated to reconcile this distance-related discrepancy is that of time, again reinforcing the principle of time dilation. So how do we make an equation that relates the time this event took in one system to the time it took in the other system? Well, we've already accomplished step 1 in our recipe. We've already defined what delta t prime was. That was with our very first example. And if you recall, delta t prime was equal to 2d divided by c. Well, our second step, therefore, is to define delta t for this latest part of the example, whilst keeping in mind that we want to arrange the components that exist in both equations algebraically such that we can substitute that delta t prime into the delta t equation. And such entails that when defining delta t, we utilize the components that are universal to both vantage points or both Cartesian coordinate systems, namely the vertical d distance that's between the flashlight and the mirror, the up and down d distance, and the speed of light as notated by the letter c. We also have to keep in mind that when we author our delta t equation, that the d and c components are arranged such that the d is divided by c. Preferably we have a 2d divided by c, but we'll see what happens. And that way we can substitute in our delta t prime and have both a delta t and a delta t prime in the final equation, allowing us to compare and contrast the time it takes for particular events to occur from two vantage points. We're also going to need a component v, the velocity of the train or velocity of the secondary coordinate system with respect to the first, and recalling how well it worked out for us before when we used distances to finally figure out our delta t prime. We'll perform a similar task here in defining our delta t. So let's start with defining how far our train went during our particular event in question. And we'll do that by applying a horizontal line to the bottom of our triangle. This is the distance traveled when the photon left the flashlight, bounced off the mirror, and returned to the flashlight. And the distance in question is just equal to the time it took for the event to occur times the train's velocity. And we're also going to need to know the distance that the photon traveled, and that will just be equal to the time it took to travel times the speed of light. And in order to combine all these different components into a single equation to see how they relate to one another, we're going to chop our triangle in half down the D line or the vertical center and just focus on the right triangle. So in that case, the distance of the hypotenuse is just half of what we defined before, so just delta t times the speed of light divided by 2. D remains the same, and our distance that the train traveled in that particular section is just delta t times its velocity divided by 2. And now that we have our components arranged inside of a right triangle, we can use the Pythagorean theorem to define their relationships. The hypotenuse squared is equal to each other side squared and then added. So now that we have an equation that relates all the components to one another, we have to somehow arrange it algebraically such that there is a d divided by c relationship, so we can sub in the delta t prime in the final equation. Also, we need to consolidate and then solve for our delta t's, and we also need a d that's not squared, so we'll have to figure out how to take square roots of things as we go along. So first step in the consolidation is to move the delta t times v divided by 2 squared over to the other side of the equation. And then we're just going to apply the squares to each individual component inside the presently squared species. At this point, we notice that our denominators are the same for the stuff on the left side of the equation, and thus we can put everything there over the 2 squared bed. Putting our work thus far to the top of the screen, we now notice in our delta t squareds that there is an opportunity to factor out this particular component, and in doing so we have achieved one of our intermediate goals, and all that's left to do now is to start taking square roots of everything that our delta t component and our d component can achieve their necessary formats. So here we are putting everything we can to the 1/2 power and then cleaning up the equation best we can. Let us again put our work thus far to the top and clean the slate, and then we'll multiply both sides of the equation by 2. At this point, we observe there is a 2d, so we're getting fairly close to getting a 2d divided by c algebraically, so we can sub in our delta t prime. And we will continue our work with dividing both sides of the equation by the square root of c squared minus v squared. And that gives us a nice delta t finally by itself. And since we are looking for that d divided by c, we're going to have to figure out how to bleed a c out of our c squared minus v squared component of the equation. And at this point, the audience may be wondering, well, how come we don't just take the 2d divided by c equals delta t prime and then just move the c over to the other side of the equation, and then that leaves us with a 2d component that we can sub in our delta t equation, thus giving us a delta t and a delta t prime all in the same equation. Well, that's great, but it looks a tad bit ugly and it's a bit cumbersome to derive any intuitive feel to the equation. There's a c in the numerator and there's a c in the denominator, so it's a little bit hard to tell when we push the v up towards the speed of light what really happens. So let us now focus on the c squared minus v squared section of the equation and see if we can't pull a c out of the hat in some manner. We could multiply the c squared and the v squared by 1. There's no harm in that. And then we'll let 1 equal c squared divided by c squared. And we'll sub that into the equation. Our denominators are the same, so again, a chance for consolidation, and we can factor out a c squared as notated. Now remember, all this is actually under a square root sign, and thus we will add our 1/2 power back into the equation, and this affords us a glorious opportunity to liberate the c squared from the square root. We'll then give our c squared minus v2 squared its own denominator, and c squared divided by c squared is equal to 1. Now we have something we can work with. Let's sub it back into the full equation. Doing so, one can observe that we do indeed have a 2d divided by c format now in our equation, and of course 2d divided by c is equal to delta t prime, and thusly delta t is equal to delta t prime divided by the square root of 1 minus v squared divided by c squared. That last little bit, I believe, is called the Lorentz transformation, or it may be part of the Lorentz transformation. So now that we have a good-looking equation, what actually does it do? Let's look at an example of 2 clocks, and one clock is stationary and the other clock is moving at 1/3 of the speed of light relative to the first. Let's pretend we're looking at a clock on Earth, and there's also a clock that's whizzing by the Earth at that velocity. If 1 hour passes on our clock that's right in front of us on the Earth, how much time is going to be on the face of the clock that's in motion? Well, we take our equation and we sub in for the v squared. We put a 1/3 c squared, and I apologize, I forgot to put some parentheses around that, but it's going to work out to 1/3 squared times c squared divided by c squared in that particular section of the equation. Then all we have to do is a few quick mathematical calculations here, and we find that delta t is equal to delta t prime divided by the square root of 8/9, or in other words 0.94. This means that if we're looking at our clock on Earth and it says 1 hour has passed, then as we look up at the clock out in space traveling by the Earth, we find by its face that only 0.94 hours have passed, or in other words, about 56 minutes have passed. That's what's on the face of that particular clock. We therefore conclude that a clock in motion runs slower than the one not in motion relative to the observer. So now you know how to construct Einstein's time dilation equation from first principles. Don't forget to check out of Woodbridge and Hedgely on Amazon.com in the Kindle section. I'll put the link in the description below. Thank you for watching and have a good rest of your day.